Okay, in part B of the interference of light, we're going to look at the two-slit interference pattern with light, or in particular with coherent light. Okay, so just to explain briefly what the two-slit interference pattern experiment involves, what we have here is just a two-slit slide, so it's like an old-fashioned slide, and it's got a series of double slits you can't really see on these small ones, but you can see on these bigger ones, you can start to see the two separate slits. And basically we shine, and I normally just use a laser pointer, we shine a laser pointer across these two slits as so. So here's me in my pantry at home because I needed a room I could make dark easily with just using a laser spirit level pointer as my laser pointer, shining it through the two slits. So this is actually through the smallest two slits, and we get the interference pattern here onto a screen. It's a little bit hard to tell with the light on, so I've turned the light off and taken that photo again. So that is what our two-slit interference pattern looks like. That's how we set it up in the lab. We could also do it with something called a Young's two-slit interferometer, which I don't have and I don't think is at Roxby, but I know Cummins have, and is another way to demonstrate this same sort of principle. And there you can also use a single slit to just make a monochromatic light coherent. But here we just use a laser because that produces coherent light on its own. Okay, so let's look at the two-slit interference and start to explain it. And there's a fair bit here, so let's just take it through step by step. So the first thing that you need to be able to do is explain why a single slit is used before the double slit for two-slit interference when the light source is not coherent. I've already mentioned that. Monochromatic light can be made coherent by passing through a single slit. And I've added this in my diagram here. So we can either get coherent light from a laser or using a monochromatic source and a single slit. Describe how two-slit interference is produced in the lab. So hang on a sec, just that goes with that. Describe how two-slit interference is produced in the lab. Well, that's what we did on the previous slide. So we saw that there on the previous slide that I just went through. You can also do an experiment with something called a Young's double-slit interferometer, which is like a special little piece of equipment that achieves a similar purpose. It's quite a neat bit of equipment to use, but sometimes it's a bit harder to visualise what's happening. So I don't actually have the equipment at Tumby. I don't think it's at Roxby either, although I might be wrong. I think the Cummins kids might have it though if they want to have a play with that. Next point that we're interested in, describe how diffraction of the light by two slits in a two-slit interference apparatus allows the light to overlap and hence interfere. So let's look at our diagram here, and I've just noticed here there's a couple of things missing, but I might just fill them in as we go. If you're clever, you'll notice that this part of the diagram is exactly the same as the top half of the diagram that we had on the previous slide, and that's quite intentional. Our two sources now, this source here and this source here, in a sense though become the two slits, the two narrow slits in the double slit slide. So this, if you like, becomes one source. Call that S1 if you like. I don't think I'm using S anywhere else. And this one becomes S2. So now the first thing that happens is as this light comes up here, goes through these two slits, is we get diffraction of the light, and the light basically spreads out like I've sort of indicated with the pointer. And then in this area in the middle, where we've got light from this source and this source overlapping, it probably is not going to diffract right about to 90 degrees, but that's just the way I've done it with the diagram using the previous diagram. We're going to get basically interference between light from this slit and light from this slit. So that combination of two slits acting as two sources, diffraction spreading out the lights, sets up the conditions, if you like, for us to get an interference pattern. Now, we saw this on the previous slide. If you look at that diagram, and I just need to add something in here that's dropped off when I've copied that distance there. L is the distance between the slits, and this would be a screen that we would have this on. What we would see is we would see areas where we had red, which was the high intensity, and then areas of black, which is where the low intensity. So on these areas here, we have constructive interference. In these areas here, we have destructive, and then constructive, and so on. So that's, in a sense, the what it looks like. You saw that on the previous slide. If we were to draw a graph of intensity of the light versus basically this distance as we go along, we'd call the distance between two peaks or two areas of constructive interference or two areas of destructive interference, delta y. These things are all defined down here. We would see that high intensity, low intensity, high intensity, low intensity, high intensity, and so on. So that's basically sketch a graph of the intensity distribution for two slit interference of monochromatic light. Don't worry about the bit at the bottom. Then explain the bright fringes of two slit interference pattern in terms of constructive interference and the dark fringes in terms of destructive. So if we go back to our path difference, if we take this point here, the path difference there to there, that one's 1, 2, 3, 4, that one's 4. So path difference of 0, which is an integer, whole number of wavelengths. If we come across to this one here, path difference, distance there, go with a blue, of 3, distance here of 4. So the path difference there is one whole wavelength, so we get constructive interference. And this is our path difference here, 0, 1. If we took the point here, we would have that length there would be 4. This one here would be 1, 2, 3, 3.5. So we would have half wavelength path difference, and we would get destructive interference. So hopefully you can see how that relates to what we just talked about, and these areas of constructive and destructive interference set up the pattern that we can see. Okay, let's get into the proof. And this is probably as challenging a proof along with the banking angle proof as what you'll do this year. So the two formulas, if you like, that we use to describe a two-slit interference pattern, so we've got our two slits here and our pattern over here on a screen, are d sine theta equals m lambda and delta y equals lambda L on D. Now we don't have to prove this second one, it's on our formula sheet, we just have to use it, but we do need to know the proof for this first formula, which is what I'm going to go through in a minute. So quickly describing this diagram, we've got our two slits, S1, S2, separated by distance D. We've got L being the distance between the slits and the screen, P0 being the point basically straight through, so we'll get a region of high intensity there because the path difference between there and there will be 0, so be constructive interference. But we want to know at some angle P, where are we going to be? Are we going to be in an area of constructive interference or destructive interference? And if you like, what order is it going to be? Is it going to be a half order difference, or 1.5 or 2.5 if we're talking about the destructive interference? So let's get into it. So at the point P here, the path difference, which we'll just call PD, is equal to the distance the light has travelled from slit 2 to point P, so this distance here, minus the distance the light has travelled from S1P, so minus this distance here. That makes sense, that distance minus that distance. And in terms of this diagram, this little bit here, S2D represents the path difference. That there is an isosceles triangle, so that length is the same as that length. Therefore, S2D represents the path difference. So next, we need to show that we know this angle here is theta, which is the angle of P. We need to show this angle here is equal to this angle here. So I've done that here. If this angle here is theta, this angle here is 90. It goes through the middle of the isosceles triangle. So it's 90 here. This angle then here is equal, so that's a 90-degree angle there as well. So this angle in the triangle, dealing with this little triangle here, is 90 minus theta. And then there's 180 degrees in a triangle, so this angle here is equal to 180 minus 90 minus 90 minus theta, and that leaves us with this angle up here being equal to theta. Okay, so now here's the tricky bit. If L, this distance here, is much greater than D, and it is when we do this experiment, this is normally, microns and this is meters, we can make an approximation that the angle S1D S2, so the angle S1D S2, so this angle in here, is a right angle, and that the triangle S1 S2D, so this triangle here, is a right angle triangle. So just to explain that approximation, if we think of this triangle here, it's a very, very long, skinny triangle. So it's much, much longer this way, very short distance here. So this angle up here is almost zero. It's very, very close to zero, which means these two angles here are almost approaching 90 degrees. So it's very close to being 90 degrees if L is much longer than D. So that is, if you like, the approximation that's essential for this proof, and now we'll go on to the final step. So finally, having established that this triangle here is a right angle triangle, we can go sine theta, so sine of this angle here equals the opposite over the hypotenuse. So the opposite, S2D, the hypotenuse is D, the distance between the splits, and S2D, as we set up here, is the path difference. S2D is equal to the path difference. So sine theta equals path difference over D. If we rearrange that, the path difference equals D sine theta. So if at the point P the waves are in phase, or there's a whole wavelength difference between the two waves that meet, that come from there and there, then we'll get constructive interference. If waves are out of phase, so half a wavelength or 1.5 wavelengths or 2.5 wavelengths, they'll be meeting out of phase, and then we'll get the destructive interference. So strictly speaking, as I've drawn that, I've got this point P having constructive interference because it's a bright band. So in a sense, this would be if m lambda equals 1. If it was a half, if P was here, the path difference would be a half, then we would be getting the destructive interference. Now, the other formula that we need to be able to use here is delta y equals lambda ln d. So this lets us, if we know this distance between two equivalent points, so two equivalent bright or dark bands, that relationship between that is equal to the wavelength times L divided by the distance between the screen. You just need to solve problems using that formula. You don't need to derive that formula. Back in the good old days, we did used to have to do that derivation, but that hasn't been in the course now for a number of years. So hopefully that's given you a good understanding of how we constructed, what a two-slit interference pattern looks like. Sorry, I do jump between double slit and two-slit, but they mean the same thing. And also that process where we use trigonometric and geometric reasoning to demonstrate that, which is in a sense what I've done on this slide.